and introduce our speaker for today. I think that's everything I wanted to say. Yeah, so I'm really pleased to welcome Brad Marston as our first speaker. Uh, Brad is a professor of physics at Brown University, and he's also the director of the Brown Theoretical Physics Center. He was a graduate of Caltech. He received his PhD from Princeton then in 1989 and did postdoctoral work at Cornell University as an IBM fellow. He's been a visiting professor at MIT, a visiting associate at Caltech, a visiting professor in Lyon, and a general member of the Kavli Institute for Theoretical Physics at UC Santa Barbara. Brad is an Alfred P. Sloan Fellow and a recipient of the National Young Investigator Award. In 2008, he was designated an NSF American Competitiveness and Innovation Fellow, and in 2010, an American Physical Society Outstanding Referee. He is also a lifetime member of the American Physical Society. He has chaired the advisory board for the Kavli Institute for Theoretical Physics and was a counselor for the APS Division of Condensed Matter Physics. And perhaps very importantly, he is the 2025 president-elect of the American Physical Society. So he will be the president of APS next year. And the last thing I'll say, I wanted to put a link to an excellent report, which I think you're going to hear all about today, that Brad kind of led the way with, and it was an APS report on carbon dioxide removal, and I put that link in the chat as well in case you're interested. The last thing I'll say is that, please stay muted during the seminar. We will take, if you have a question, you can type it in the chat. If it's really important, maybe I'll interrupt Brad and we can read the question, but otherwise I'll read down the list of questions at the end, and then Brad can answer them. All right, so Brad, why don't you go ahead and share your screen?
All right, thanks very much for that kind introduction, Justin. So yeah, it's been a real pleasure to see the topical group on the physics of climate evolve over the years. I was there at the start when we were first setting it up, and it keeps on getting more and more ambitious. This seminar series, I've been enjoying listening to a lot of the speakers and then the sessions at the March meeting. So if you aren't a member of the GPC, but you're at all interested in climate, you don't have to be a climate expert, consider joining. Because it's a really, I think it's really a wonderful thing that APS has. So I want to tell you today about atmospheric carbon dioxide removal, a physical science perspective. This is a picture of a reconstruction of carbon dioxide emissions on Earth, mainly in the northern hemisphere, this brownish color. But also carbon dioxide being absorbed by the oceans, particularly around Antarctica. That's the greenish color, or in the tropical forests. Just to drive home the point that most of the emissions are in the northern hemisphere, but the Earth is already just naturally absorbing some of that carbon dioxide, about 50%. And what this talk is about is looking at the possibility that that could be artificially enhanced in some way to speed up the removal of carbon dioxide. So I'll be talking about this report that that came out earlier this year, I think. It is both a publication of the APS panel on public affairs, but it's also a publication of the journal PRX Energy. So you can find it in either form. The PRX Energy one is sort of the typical APS journal format. And the effort in putting this together, which took several years, was really led by Waddy Taylor at MIT, who is a theoretical physicist who's working on many different things. He's co-author of the textbook, The Physics of Energy. Bob Rosner, former APS president and also former director of Argonne National Lab. Jonathan Wurtel, at Berkeley who works on plasma physics and trapping of antimatter at CERN, looking at the properties, for instance, of antihydrogen, and myself. And that's just to say that none of us are experts in this area, but we decided it was worth to take a look at the different ideas that have been proposed and in some cases are being tested in the field for removing carbon dioxide from a physical science perspective. Now, this isn't the only perspective one needs to take. There's also very important questions about the economics of this, the politics of this, um, that have to be answered before anything is really deployed at a large scale. So we, being physicists, wanted to just focus on the physical science aspects. And we're not proponents for this. So we're trying to take a look as balanced as we can. And you'll see that it's not obvious that this should be done. There are many questions, obstacles, but we wanted to try to take a fresh look. There's been a number of reports written about this, including by the APS panel on public affairs about 12 years ago or so. But the field has been moving along rapidly, and we thought it was worth looking at again. So as I'm sure everyone on this the Zoom call is aware, the carbon dioxide levels in the atmosphere have been rising rapidly due to mainly human activities, burning of fossil fuels, deforestation, production of cement, and so on. And so this is the famous Keeling curve showing the concentration of carbon dioxide in the atmosphere. And the reason I show this is that it's also showing some other interesting features. First of all, we see the seasonal cycle, the oscillation, the red oscillation in that curve, which is showing that the Earth is absorbing carbon dioxide from the atmosphere, causing an actual drop in the atmospheric concentration over the springtime when plants are growing in the northern hemisphere, where most of the land plants are located, and then releasing it in the fall when they're dying back or their leaves are decaying. So we see that there's already this interesting flux of carbon dioxide going on naturally in the Earth system. And then if we look at the dark line, which removes the seasonal cycle, of course, there's the steady growth, but there's also some interesting fluctuations, which are largely due to the El Nino influencing the carbon uptake by the Earth. So during El Nino years, there can be more forest fires in the tropics, for instance, that release carbon dioxide into the atmosphere. So there's a lot of interesting processes already visible in this plot. Now, when we look at the carbon reservoirs in the Earth and the different fluxes, then the atmosphere has this 875 gigatons of carbon, which if we convert that to carbon dioxide, because of the additional mass of the two oxygen atoms in the carbon dioxide molecule is 3,200 gigatons of carbon dioxide. The ocean contains much more. So it has 37,000 gigatons of carbon. The soils have thousands of gigatons of carbon. All of these things have fluxes back and forth between the different reservoirs. And our input of carbon from burning of fossil fuels and other contributors is on the left side. So we see 9.6 gigatons of carbon currently being released into the atmosphere from burning of fossil fuels and deforestation and so on. And so if we convert that to mass in carbon dioxide, that's about 36 gigatons of carbon dioxide. And so I'll mainly be using as my mass unit for the rest of the talk the mass of carbon dioxide rather than the mass of of carbon. Now, another fact, of course, is that temperature has been rising. So this is a reconstruction of Earth's surface temperature, average over the entire Earth, going from the 1940s to the present, with the different colors indicating the decade, and then the year, the months of the year in the horizontal axis. And we see that of course, there's been this steady rise in temperature, but also a jump that occurred last year, well, 2023 to 2024, that's still not fully, I think, understood why there was a sudden increase. But I'll maybe touch on one possible contributor to that at the end of the talk. We also have another plot here showing that there's some interesting structure in that growth in temperature as a function of latitude. We have the Arctic amplification visible at the high northern latitudes that you can see at the top of this plot. That's something that was actually predicted by very primitive climate models back in the 70s by Manabe and Weatherald, and then realized in the actual climate system. So that's the problem, of course, that we're seeking to address if we want to absorb carbon dioxide from the atmosphere. This is a form of trying to modify the Earth system, but directly getting at the root cause of climate change, or at least much of climate change, by removing carbon dioxide, as opposed to, say, solar radiation management, which is a more of a band-aid, trying to reflect more light, which again, I'll come back at the end of the talk. And I'm not going to talk about methane, which is another important greenhouse gas. There are some thoughts about trying to remove methane from the atmosphere, but this is much less far along, and more attention has been paid to removing sources of methane and also chlorofluorocarbons, other greenhouse gases. So I'm just going to concentrate on carbon dioxide today. So let me begin with findings. What I'll argue is that carbon dioxide removal, CDR, requires extensive energy and/or material inputs. But this isn't necessarily a showstopper. So if you're willing to put in extensive effort, then probably this can be done. But I want to convey the scale of what needs to be done. Action, even with robust emission reductions, large-scale CDR may be necessary to maintain atmospheric CO2 levels within desired limits. And indeed, the IPCC has argued that it was actually required. Thus, it's worthwhile to pursue a targeted and prudent research program and do some small-scale deployments to learn from that experience. On the policy side, economic and policy frameworks for carbon management need to be designed and implemented to facilitate balancing the costs and benefits of large-scale CDR and emission reduction strategies. This is going to, if this is pursued, it's going to be very expensive, and so decisions have to be made about trade-offs. If you do this and you can't do something else that you might want to do. We'll talk a little bit about that. So there are a number of ideas, approaches to trying to remove carbon dioxide that's already in the atmosphere. And I want to emphasize, I'm going to focus on that problem and not the problem of taking a directed stream of carbon dioxide, say from a coal-powered power plant, and doing something with that instead of releasing to the atmosphere. So that's another set of technologies. There's some connections. But this is actually a much, I think, a more difficult problem because, as we'll see, there's a severe thermodynamic penalty once the carbon dioxide is in the atmosphere. So the different approaches that I'm going to talk about today beginning from the left side of this plot, are direct air capture, building machines to remove carbon dioxide from the atmosphere. Um, and then ecologically based CDR, so growing plants typically to absorb carbon dioxide, perhaps converting some of that plant mass to energy. That's this bioenergy, carbon capture and storage, BECCS, that you see there, where you would now capture that concentrated stream, which again, I'm not going to really talk too much about, but use the plants to absorb, assume that that can be done, use the plants to absorb carbon dioxide and also produce some energy from that. Then there's ERW, which is enhanced rock weathering. The idea of accelerating the natural carbon cycle on geological timescales, trying to accelerate that so that the weathering of rock can absorb carbon dioxide on human timescales. And closely related to that is ocean alkalinity enhancement, OAE, where we're using the ocean and adding material to it typically, or perhaps using electrochemistry to alter its chemistry in such a way that to enhance its ability to absorb carbon dioxide. Now, one of our key findings in this report is that these different strategies can mostly be classified under two different categories. And the first category I want to talk about is what we call cyclic. And cyclic is, you can think of it almost like a heat engine. It's energy intensive. It's going to be using energy to remove carbon dioxide from the atmosphere. And so if you want a kind of simple analogy, it would be like if you were in a rowboat that's has sprung a leak, it's filling with water, that's the carbon dioxide, and you had a sponge, you would be using that sponge to soak up some of the water and then squeeze it overboard to remove that water, requiring energy, and then using that sponge over and over again to try to mop up this water that's coming into your boat. So the basic idea is we have this stream of the air coming into a machine that has has the carbon dioxide, 420 parts per million of carbon dioxide, and then some chemistry happens with energy input to remove that carbon dioxide from the atmosphere, at least most of it, and then the carbon is in the material, and then that material is then persuaded to release the carbon dioxide in a pure stream, which that can then be sent underground or used for making plastics, making materials. So this would involve some material, and I'll give you some examples in a moment, which is used over and over again with energy input to accomplish this. And how much energy is required. So the reason, well, by the way, that energy is required is simply thermodynamics. We have this dilute concentration of carbon dioxide. And so if we want to just concentrate it up to 1 atmosphere, 100% at 1 atmosphere, so a million parts per million, from 420 parts per million, then just from basic thermodynamics, we know how much energy is required at a bare minimum to accomplish that, to basically reduce locally the entropy of this mixture. And that turns out to be 120 kilowatt hours for every ton of carbon dioxide. So 1 ton of carbon dioxide would be about the amount of carbon dioxide that you would emit if you were flying coast to coast in a commercial airplane that you would be responsible for. So you'd have to pay a penalty of 120 kilowatt hours to try to concentrate that carbon dioxide into a pure stream. So let's think about how much energy would be required to capture 1 gigaton of atmospheric carbon dioxide. So that's only 3% of our annual emissions. We have that 36 gigatons of carbon dioxide per year. So let's, as a comparison throughout this talk, let's just think about trying to remove 3% of that, 1 gigaton of carbon dioxide. So according to this formula, you would need, at a bare minimum, 14 gigawatt years of energy. So think about 14 nuclear power plants running for a year to remove that gigaton of carbon dioxide. That's at a bare minimum. A more realistic number would assume that, well, we have chemical processes. Maybe we're doing thermal cycling of this material. There's going to be inefficiencies associated with it. So maybe the best we can do is only 3 to 10 times that thermodynamic minimum. So now we're talking about 42 to 140 gigawatt years of energy. That's that middle bar. And on the right is the total electrical energy production by the US in 1 year. So 484 gigawatt years. So we can see that just to remove 3% of the atmospheric carbon dioxide by this direct air capture means that we would have to use a considerable fraction of the US electrical power output to accomplish that. And clearly, you don't want to produce that power by burning coal. That would be really just undoing a lot of the good from this if you could even implement this. So this is a schematic of some different machines, different views of how you would absorb carbon dioxide. I'll show you pictures of some real pilot plants in a moment. So again, to remove this 1 gigaton of carbon dioxide, you need a minimum of 14 gigawatt years, which is like all of Virginia's electrical consumption. But more realistically, it'd be more like the electrical consumption by the state of California at a minimum. If you wanted to power this with solar panels, then you'd need something like 4,000 square kilometers of solar power. So you have to have a large intake. And you also need machines that have a scale sort of on the size of the Great Wall of China. So if we assume 2 meter per second flow rate through the machine, and let's say the machine is 20 meters tall, you need something like 1,000 kilometers in order to get that much carbon dioxide just passing through air. And it turns out that this is about the volume, 1 gigaton of carbon dioxide is about the volume of air over the state of Georgia. So imagine processing the volume of the air over the state of Georgia per year to get that 3%. Nevertheless, despite these daunting numbers, there are quite a few trials in the field working to demonstrate that this can be done, at least at a relatively modest scale. And so there's a website that's keeping track of all these. We're going to look at a couple deployments here. So this is the one that's probably gotten the most attention. This is the Mammoth plant from Climeworks in Iceland. This is their second generation plant. They're taking advantage of the relatively cheap geothermal energy in Iceland, plus the warm basalt underneath to send a concentrated stream of carbon dioxide down into the ground, where it then reacts with the warm basalt and forms carbonate minerals. So it gets locked in place. So the capacity of this machine is supposed to be around 36 kilotons of carbon dioxide per year, 36 kilotons. That means that you would need 1 million of these machines to absorb all of our emissions of carbon dioxide into the atmospheres. And so that just gives, I think, a sense of the scale of the problem. And this machine is, as I said, built in a rather optimal location. That's why it's in Iceland, taking advantage of that cheap energy and easy access to warm basalt for storing the carbon dioxide stream. Here's another pilot plant that's being built by a company called Heirloom, and it's taking advantage of a solid reaction. So using quicklime calcium oxide to react with carbon dioxide to form calcium carbonate. And so these trays contain the calcium oxide, quicklime, um, that air is being blown through, maybe with some moisture, reacting to form calcium carbonate, which is basically limestone. Then the limestone is removed by robots from pulling these trays out and baked in at high temperature to remove the carbon dioxide, basically reverse this reaction. The carbon dioxide stream is then can be sent down underground, maybe to a in I think this one is in New Orleans or in Louisiana rather, and the stream is sent into one of these salt caverns, if I remember right. So this is the cyclic process going back and forth between quicklime and calcium carbonate. In the heirloom machine that I showed you earlier, I think it's a liquid sorbent that is being used as the active material. And there's a lot of research going on to develop new materials for absorbing carbon dioxide and increasing the energy efficiency. Okay, so a lot of effort, a lot of investment has been going into those direct air capture machines. But this other approach, which we classify as in our second classification, we call once through. And it tends to be very material intensive, but usually less energy intensive. So in our analogy of draining water from a rowboat, this would be like using a roll of paper towels where we're soaking up the water and we're just throwing the towels, the wet towels overboard and not worrying about recovering them. So typically this involves extracting some raw material that is already out of equilibrium with the atmosphere. And I'll mention some different rock types that are favored. Grinding it up very finely to try to increase its surface area so that it will react fast enough with carbon dioxide in the atmosphere or also in soils. Maybe plants are absorbing carbon dioxide and enhancing the concentration within the soil, and then that's enhanced carbon dioxide is reacting with this material and forming ions, carbonate ions and bicarbonate ions that then flow off the land into rivers and eventually, it's hoped, the ocean. So now our main concern is how much material is needed to accomplish this goal of, say, capturing 1 gigaton of atmospheric carbon dioxide. And if we had 100% efficiency, unrealistically, then with a material like a mineral called forsterite, then you would need about 1.5 gigatons just from stoichiometry to remove that 1 gigaton of carbon dioxide. More realistically, again, we're not going to be that efficient. There's going to be various losses. Some of the material won't react. Maybe we need 3 to 15 gigatons. And if we just compare those numbers to the amount of crushed stone produced in the United States, that happens to be about 1.5 gigatons of crushed stone, although a lot of that stone is not crushed as finely as one would need for this. So enhanced rock weathering refers to spreading this ground material like ground olivine, other material, other ground rocks over land area, typically over farmland, where farmers might enjoy some co-benefits that may improve the soil, add minerals to the soil. So farmers might, it's hoped, want to do this anyway. So we're getting around the second law of thermodynamics because the materials are already out of equilibrium with the atmosphere. Of course, the second law still holds, but we're not limited by that. But we do have to put some energy into mining and grinding the rock and then distributing this large mass. So just to emphasize that this happens naturally, this is a view of a mountain in Northern California. It's called Marble Mountain. It's basically really limestone. And what you're seeing is that water from rain or snow contains some dissolved carbon dioxide from the atmosphere. It forms a weak acid, that carbonic acid, which then reacts with the limestone and is etching it away. And you can see these rivulets at the bottom of the picture. So carbon dioxide with H2O gives this carbonic acid, and then the carbonic acid reacts with the calcium carbonate to give you these bicarbonate ions plus calcium ions. And then it's hoped that those bicarbonate ions will go into rivers and then into the ocean. So this may be a little bit counterintuitive because many of you have probably done the classic experiment of mixing vinegar or pouring vinegar on limestone, and you see bubbling happen because there's carbon dioxide that's being released, and you get this fizzing reaction. The difference here is this is a very weak acid, so that the reactants stay in the form of bicarbonate ion, so they stay in solution, and that's the trick behind these ideas. This is just showing some kids playing with on the surface here at these rivulets and some of the caves that have been formed by dissolution. Another type of rock that's been the subject of a lot of attention are mafic and ultramafic rocks. The mafic just stands for these rocks contain iron and magnesium. And so what you're seeing here is a rock called peridotite, which has a lot of olivine in it. There's a large amount of this in certain locations in the earth. This one's in the Klamath Mountains. And then down in the lower right panel is basalt at Devil's Postpile National Monument. And all of these minerals can react with the carbon dioxide. This is forsterite, or basically olivine, magnesium, silicon, oxygen reacting with carbon dioxide. If we did this in the absence of water, it gives magnesium carbonate plus silicon dioxide, quartz, and some energy. It's exothermic. But if we do it in the presence of water, then we can actually absorb twice as much carbon dioxide if we keep the carbon ions in solution in these 4 bicarbonate ions. So that's the optimal situation. So water is a very important part of this. So to give you a sense of scale, this is a basalt flow, a lava flow in Utah, the Ice Springs basalt flow, and its volume corresponds to about 1.5 gigatons of basalt, which could absorb potentially, if it all reacted, 0.5 gigaton of carbon dioxide. So you need sort of 2 of these giant flows. You can see the scale of the flow with respect to these crop circles in this satellite view. And on the right is just an old mining machine. This is actually an Aspen in the mining museum, which grinds up rock. And just to say that this technology is very mature. Now, if you're interested, you can do a demonstration of this, and we've been doing this for a class that I'm teaching. There's a nice article that just came out in Chemical Education. What you can do is you can take a plastic bottle and put some water in it, and put in some ground basalt or whatever your favorite rock you want to use is, and fill the space above with carbon dioxide. You also want to do, of course, a control run with ordinary air. And after about 7 days, then the bottle contracts because the carbon dioxide is reacting with that with the basalt and forming these bicarbonate ions. So we can see that we really can speed this reaction up to sort of human timescales. This is another material called wollastonite, calcium, silicon, oxygen. And I show this, we're going to come back to this at the end of the talk because notice its color. It's a whitish color. It also reacts with carbon dioxide, and it's being spread on farm fields, not well, it's being used in some trial runs for enhanced rock weathering, but also farmers are using it to enhance their soils. Now, I mentioned that these ions go into rivers, which hopefully go into streams, and hopefully go into the ocean eventually, where those carbon ions will stay out of the atmosphere for a long period of time, but they may escape along the way. And you can see here in this stream in Southern California, this white material that's on the rocks has come out of solution as the stream has flown down. So this is something that needs a lot more studying. And in general, the whole science, the whole geochemistry of how this all works is poorly understood. And there's a lot of work going on, but a lot more work needs to be done to see if this is really a reliable approach. Now, another approach along this lines is called ocean alkalinity enhancement, where these minerals could be spread, ground up again and spread over the ocean to try to increase the alkalinity of the ocean. So the alkalinity is something that I've been sort of hinting at. It's basically a measure of these conserved ions, the sodium ions, the calcium ions, minus the chlorine ions. So it's a charge-weighted sum of the concentration of these ions that tells us about the potential of the water to absorb carbon dioxide. So we want to increase, for example, the calcium ions in the water so that the species on the right side of this equation are being absorbed by the and staying in solution. So the bicarbonate and carbonate ions in particular. So the alkalinity is the key chemical measure of this capability. Now, when we were first starting this work, I thought I'd do a little experiment to understand better what was going on. And since I'm a theorist, I actually asked my wife, who is a biologist and has access to chemistry, to do this for me. So what we did is I thought, well, I'll just take some sparkling water and add some, increase its acidity. I'll try to decrease its alkalinity by adding hydrochloric acid to it, and surely the carbon dioxide will come out. And so let's see what happens here. So the flask on the left has Perrier water in it, and my wife is going to add some hydrochloric acid, and on the right, she's just going to squirt some ordinary water in. So, okay, she's going to squirt the water in. And if you look, you can see some little bubbles just from the agitation occurring. And now over on the other side, she'll add some, I think, 1 molar hydrochloric acid. And there's no difference. So I was immediately humbled in my understanding of what was going on here. Basically, in both cases, the agitation removes some carbon dioxide, some bubbles form, but no more when we add the hydrochloric acid to the Perrier water. So I asked some chemists, what's going on here? I don't understand. I thought if I increase the acidity or decrease the pH of this the water that has carbon dioxide in it, it's going to release carbon dioxide. And I started to feel a little bit better when they couldn't answer this question. So what's the resolution here? Maybe think about that for a moment, and maybe we'll talk about that at the end of the talk, because there's actually a simple resolution and it teaches us something important about this. Actually, I'm going to tell you right now because then I forgot the next slide is actually going to reveal this. So the difference is that Perrier water or carbonated water is already has a low pH. It's already rather acidic. So adding hydrochloric acid doesn't actually shift things any more than it already is. In fact, the carbon dioxide is already out of equilibrium. And that's what we saw on the right-hand side, because just agitation, or as everyone knows, if you just leave this out, it'll go flat. So all we're really doing is just driving the carbon dioxide out by the agitation, and adding the acid doesn't really affect things. And that's expressed by this plot here, where pH is along um, the uh, the horizontal axis. The pH of ocean water is in this gray region. It's in a bar because we've been making the ocean more acidic. So we've been moving from the right side of that gray bar to the left side. And then the species, the speciation of dissolved carbon dioxide, CO2 star, bicarbonate ion HCO3 minus and CO3 minus double minus, so carbonate ions are shown here. This is just the equilibrium chemistry. And what we see here is that for the pH levels of the ocean, most of the ions are in the bicarbonate form, and that's where we want them to stay. But if we did make an extreme change in the pH towards the left side, towards the acid side, then the carbon dioxide would start coming out. And the Perrier water has a pH of somewhere around 4 or so. So it's already in this regime where the carbon dioxide is already in just dissolved form, not in the ionic form. So in order for these ocean alkalinity schemes to work, then we have to really concentrate on the ocean circulation. If we add material to the ocean, will it dissolve before it sinks? Will it have enough time to absorb carbon dioxide, to change the alkalinity of the surface waters? And then perhaps that water will sink in the best case scenario, but maybe it will come back up. It's like with the enhanced rock weathering, it is a complicated problem. So now I'd like to talk a little bit about some of the ecological approaches. Regrowing forests is one idea. So in the city of Arcata, up in the redwoods of Northern California, you can buy for $37 a metric ton an offset. And they have a old growth forest. It's not an old growth forest. It's a second growth forest, but it was logged about 100 years ago. So the second growth trees are already quite large. And as long as this forest is preserved, doesn't burn down, isn't cut down, arguably this is a relatively long-term storage for carbon dioxide. You can't just go log a forest, try to capture that carbon necessarily from the log trees and then replant it and expect that it'll work in the same way. So just even doing clear cutting will tend to release a lot of carbon into the atmosphere and through the soil erosion. So this is kind of the ideal situation. And in fact, redwood trees sequester the most amount of carbon per square meter of any ecosystem on Earth. So that represents one of these biologically based approaches. You could also grow crops, maybe some fast-growing grasses, and then bury the material once it has grown and absorbed carbon dioxide. And then, as I mentioned, perhaps you would view this material as too valuable to bury directly. Maybe you want to get some energy out of it first, and then take that stream of carbon dioxide and sequester it somehow. The problem with these approaches is that they're very land intensive because photosynthesis is a pretty inefficient way of converting light into energy and capturing carbon dioxide. Then you need a lot of land, and that competes with other uses for the land, such as agriculture or, say, ecosystem restoration. And also, I want to emphasize that the durability of this needs to be examined carefully. Again, going back to the forest example, you guaranteeing that that forest really is going to be there 100 years from now, 1,000 years from now, in the face of climate change, population growth, and so on. These are some of the challenges, but these are some of the least expensive approaches. And in general, some ecosystem restoration is probably a good thing to do anyway. So if you get some co-benefits from carbon dioxide removal, so much the better. All right, so I'm nearing the end of my time. I just want to emphasize some points here that measurement, reporting, and verification, which goes under the acronym MRV, really needs to be done, especially for these once-through approaches to make sure that they're really working the way that we want them to work. We can take a number of approaches to try to deal with deal with climate change due to rising carbon dioxide in the atmosphere. The emissions reduction, that's the easiest thing, really, and much easier than trying to remove it from the atmosphere once it's already up there. So really, the effort should be spent on emissions reduction. That's I think, the top line message from our report. Using CDR, that may be possible, but as we've seen, the scale is just enormous. Then there's solar radiation management, trying to cancel out the radiative forcing from atmospheric CO2 without directly addressing the atmospheric CO2 issue. That, of course, is rather problematic. There's many concerns about that. It probably can be done, but there may be many side effects. There's all sorts of questions about governance and the safety of this approach. And finally, there's the strategy of basically adapting to the climate change. So certainly that's going to happen at some level. So again, I don't want to go through this in great detail, but we've seen that large scale CDR requires substantial energy inputs and massive material infrastructure. It might be desirable to do in the coming decades, but efforts to reduce carbon emissions should not be compromised by the possibility of future large-scale CDR. So that's really the moral quandary here. We don't want this possibility to short-circuit efforts to reduce carbon emissions. And then some other points. So let me just take a few minutes to just say some things of where my own research going beyond this report has led. So, of course, in thinking about this over several year time, a number of questions, many questions rose, scientific questions that deserve attention, I think. And I'll tell you about one that we're working on. So just going back to this sudden increase in temperature recently, one possible contributor to this is the cleaning up of emissions of from dirty diesel fuel powering cargo ships across the ocean. And you could see these tracks from clouds that have been nucleated by the particles emitted from this dirty fuel being burnt. So that's been increasing the albedo of the Earth slightly. But around the year 2020, there was an international agreement to clean up this oil. And so the pollution that's been nucleating these clouds has been reduced. So the Earth is absorbing more radiation, and that's probably leading to some of that sudden spike in temperature, but not all. So if we go back to thinking about modifying large surfaces of land, then there are we have to ask how does that affect the albedo? And if we just look at, for example, this grassland and redwood forest here, we see that the redwood trees are much darker than the grassland. So if we were to plant redwood trees everywhere, we would darken the land. And it's been argued that that can cancel out about 30% of the effect of absorbing the carbon dioxide. If we go to thinking about enhanced rock weathering, say spreading this whitish wollastonite over a surface, that's going to change the albedo in the other direction. That's going to reflect light. And or if we think about ocean alkalinity enhancement, we might stimulate the formation of plankton that could change the reflectance of the ocean. And here we're seeing a eddy in the ocean that has trapped some diatoms that are reflecting light out into space, visible from satellite. So we can make a simple calculation of the radiative impact from a change in albedo and compare that to the radiative impacts from the absorption of carbon dioxide by, say, enhanced rock weathering or ocean alkalinity enhancement, or growing trees for that matter. And we can easily argue that the albedo effect can dominate at least over the period of years and decades. So perhaps the material continues to react with carbon dioxide for some long period of time, but the albedo effect is immediate. And so if we have a simple model for how much carbon dioxide is absorbed, say, linearly over time, then for typical numbers for the amount of carbon dioxide that might be assumed from actually quite good enhanced rock weathering, then we could find that over years or decades, the signal will be dominated by the albedo change at first. So this might be a form of surface albedo management, SAM, that has a cooling effect in the short term that then leads to a long-term benefit in terms of absorbing carbon dioxide. At least that we could dream about that as a possibility. And since we're talking about very large areas, and we're talking about millions of square kilometers, then normally we don't think about surface albedo management as a viable possibility for cooling the Earth, but here we're talking about, say, a substantial fraction of the land that's been used for agriculture. And so if you're interested, we have a preprint, and we're actually going to be doing some field trials here in Rhode Island at the University of Rhode Island, which is our ag school, to make some measurements of albedo and see just how big of an effect this is. Okay, so some closing thoughts. CDR is not a replacement for decarbonization, it's a supplement. The scale of any effort to do CDR should not be underestimated. It requires just enormous scale and a multi-decadal commitment. And it's only worth even really contemplating if you have a idea that can be scaled up to such a size that it can affect the whole atmosphere in a serious way. And it's crucial to understand how to verify this and look at risks and potential impacts of CDR approaches. And then the question of who decides to do this and who pays is not something that we leave completely unaddressed. So thank you for your attention.
All right, great. Thank you very much, Brad. We had a few questions, one that was sent to me. So I'll encourage you to put your questions in the chat and I'll read them out. The first one was sent directly to me from Michael Cloyter. Are there any advantages to direct air capture over point source capture? For example, flue gas contains 100,000 parts per million of CO2 compared to the 420, obviously, in the atmosphere.
Right. So the thermodynamics are much more favorable for the flue gas capture. Since you have a concentrated stream, you might have to deal with some other gases that might be corrosive. And there have been pilot plants built to attempt to demonstrate this. I haven't studied this very carefully, but my sense is that they haven't been so successful, and there have been technological problems with it. On the other hand, you can argue, well, this is just encouraging the continued use of fossil fuels. Maybe there are places where it's really hard to eliminate those fossil fuels, or in cement production where you're trying to capture this carbon dioxide. So the thermodynamics are much more favorable, but in this report, we wanted to focus on this more ambitious problem.
Great, thank you. So next question is in the main chat that everybody can see. Should we think of atmospheric CO2 as a well-mixed system? If not, can we take advantage of concentration gradients to locally remove CO2?
Yeah, it's pretty well mixed. So that the figure I showed on the very first slide exaggerates the idea. It makes it look like there's this huge blob of CO2 headed to the southern hemisphere. There are concentration differences. If you look at the long-term record, for example, from Mauna Loa, Hawaii compared to Antarctica, Antarctica is a little bit behind, but we're only talking about like 1% or so. So it's very well mixed, and apart from very localized sources like around a power plant, then I mean, from that point of view, you could say, well, capturing the emissions from a power plant is taking advantage of it. But other than that, it's very quite uniform.
Okay, great. Next question. If we remove CO2 from the air, will the oceans outgas CO2 in order to maintain equilibrium with the atmosphere?
Right. Yeah. So that's a good question. If we could dream of say we were able to implement CDR at such a scale that we could start bringing down the carbon dioxide concentration in the atmosphere instead of slowing the rise of it. Say we wanted to go from 420 to 400. Then, so right now, the oceans and the land plants are helping us because they're absorbing about 50% of our emissions. So that, makes our task of slowing the rate of growth easier since the nature is already doing some of the lifting for us. But if we're trying to just pull it down, to actually decrease the total amount, then it acts against us. It makes the problem twice as hard because now the ocean will start outgassing in the mixed layer with the atmosphere. So now we're fighting against not just the carbon dioxide in the atmosphere, but also carbon dioxide in the oceans.
And then there was a follow-up. Any prediction when the oceans will be saturated with CO2 and bicarbonate and begin to outgas?
Well, so it depends on where you are in the ocean. There are places where it is saturated and there is outgassing. Yeah, so it really down in the Antarctic, there's a lot of absorption of carbon dioxide. Down in the equatorial regions, there's some outgassing. The net is that there's absorption. So that could be expected to change gradually as the climate changes.
Okay. Uh, there's no more questions in the chat, but if anybody has one, please go ahead and put it there. So just following up on that oceans question, that we learned about a few different ways to get or to precipitate the carbon out of the ocean. Would it be better or would it be useful for people to start thinking about more large scale ways of getting carbon out of the ocean or get it to precipitate and then just have the ocean continue to absorb from the atmosphere, and that would be the sink.
Right. Yeah. So one approach I didn't mention is called direct ocean capture.
Yep.
And that's basically to have machines like the air capture machines that are processing ocean water and are changing the alkalinity or removing carbon dioxide from the ocean water, again, requiring a large energy input. And the advantage of that is that the concentration of carbon dioxide in the ocean by volume is higher than it is in the atmosphere. So you have more molecules per volume. Of course, you're dealing with a much larger mass also per volume, about 1,000 times more massive per unit volume. But there are some efforts to go to along those lines. There's also efforts to change the electrochemistry of the ocean by electrochemical means, again, using power input, changing the alkalinity of the ocean. But then all of these ideas are using the ocean essentially as our sink instead of the surface, instead of land surface. So I think these are interesting things to pursue.
Wonderful. So we are at the hour, so this might be a good time to stop unless there are further questions. I'm going to post two links in the chat one last time. The first link is to the seminar series webpage in case you're interested in joining us for future talks. You can register for them already. And the other link is directly to Brad's report with his co-authors on carbon capture. All right. Well, thank you very much for joining us, Brad, and we hope
Thank you.
everybody has a good rest of their day.
Bye.